In the last video for Chapter 2, we're going to talk about switch hierarchy. Cisco has come up with a way that they recommend we put switches together in our organization to be the most efficient that they can be. Here is their recommendation. They have very, very fast switches up here called core switches, and then medium rate switches here called distribution layer switches, and then down here the slowest ones being access layer switches. Up here is the actual backbone of our organization at this router. Down here at the bottom is where we would actually attach PCs, servers, printers, all those end user devices. These are attached to these access layer switches. And you can see that what I've done is I've added a bunch of lines between these switches. Now, not all of them. There's no line here, there's no line here, there's no line here. I've left a few out. You don't have to have it perfect. But what we have is a way for traffic to get from point A to point B in the fastest possible method. Now, just because these are slower switches doesn't mean that it's not the fastest method to get from A to B, because there is a time delay, say, between this switch and this switch. But even a greater time delay if I have to go to this one, then this one up here, and then this one down here, and then this one, then this one, then this one, and then down. That would take longer. It's very similar to going to the store. It's faster for me to take a back road than to take the freeway, because I have to go out of my way to take the freeway. Even though the freeway is faster, it's faster for me to take the slow route than it is to take the fast route. All right? So that's how this works. Now, this does provide one nice thing, redundancy. Let's say, for example, that this right here, this line went down. Well, I needed to get from here, from 1 to 2. Well, I still have a way there if I have to. I could now go up here, and then here, and then here, down to here, over to here, and then down. So I do have a way to get there. I have a redundancy built into this, which is really, really nice. However, I do have another problem. We haven't really talked yet about how switches function in any great detail. But when a switch is learning about the devices, the other switches and the PCs and so forth that are attached to that switch, that learning process requires switches to send information out to all the devices in order to learn who's attached to that switch. So let's say that I'm trying to get from, let me see, from here, 3, to something over here, 4. All right, here's the problem. This switch doesn't know where 4 is yet because it hasn't discovered it. So it's going to send data over here asking, and it's going to send data up here asking. It's going to send it out every port on that switch. Now I'm going to come over here because this switch doesn't know, what to do with it. So it's going to put it over here. That one's going to send out to all of its ports, which is going to send out to all of its ports, and you can kind of see what's going to go on here. That's a router, not a switch. You can kind of see what's going on here. Things are just going to go around in big loops like this, right? I'm going to have things going in every direction until my data just goes around and around and around here, and around and around and around here, and around and around and around up here. I've got all these loops, and these loops are going to cause what we call a broadcast storm. Broadcast storm, in which things just start flying everywhere, and it slows the system down to next to nothing, if not crashes it altogether. And in fact, broadcast storms are one way that we can cause what we call denial of service attacks. We can actually shut something down by causing a broadcast storm. Shut an entire network down by making a broadcast storm. So we have to have a way to get around that. So how do we do that? Well, let me go over here and use the eraser and erase some of these lines here for a moment and talk about what I would do to prevent this problem of these loops, and thus prevent the problem of broadcast storms, because we don't like broadcast storms, right? So here's what I do. I decide that between any two of these switches, I'm only going to allow one connection to work. So in other words, let me find a good example here. Okay, in this switch right here, I don't know, I'll just call this switch Fred. I don't have a better, oops, I didn't turn on the, I got to go back and turn on my ink instead of the eraser. I guess that would be helpful. So Fred here. Fred has various ways to get to any given point. Fred could get, say, to this switch down here. It could get here this way, like this. It could get here this way, and it could get here this way. It's got three different ways that it could get from this switch down to this switch. So what we do is we block some of these, and we only allow one way, the fastest way, to get there. So that now this becomes the way that Fred uses to get to that switch. We call this spanning tree protocol, because we have kind of a tree structure here, and we can turn off certain links and only allow certain other links, so that everything only has one way to get to any other given place. And then if that goes down, if this for some reason were to go down, then one of these other ones would open up and allow traffic to go another direction. So spanning tree protocol is the way that we deal with that. And just kind of self-setting, I mean, there are things that you can do to spanning tree protocol, but pretty much it sets itself up on switches and just kind of runs on its own. So switches are kind of smart that way. All right, that's it for this hierarchy. Just remember the core distribution and access layers, that it does allow for redundancy, but can cause these broadcast storms and these loops to occur, and that spanning tree protocol is the way around that.